Hi everyone, and welcome to my presentation on how to compute the inertial velocity of a point fixed in a rotating frame. So the first example that we're going to see today is the wingtip of an aircraft, and we want to know how to compute the inertial velocity of that wingtip, and that is with respect to the airframe. So the first thing that you need to do is to establish your reference frames, and that is E, the inertial frame fixed to the ground, and then V, the body frame fixed to the aircraft. The body frame moves and rotates with the aircraft. And then your position vector r tip can be broken down into RV plus small r tip. And we know that the inertial velocity of the wingtip is going to be equal to the derivative of the position vector with respect to time. So all you need to do is to take the derivative of the vector components with respect to the airframe. So that is going to give you the translational velocity v of the aircraft with respect to the airframe plus dr tip over dt with respect to v, and that is the body frame. And that is going to be equal to 0 because that distance doesn't change over time. It is a rigid body, so that is going to be equal to 0. And then you have the contribution of the rotation of the body frame with respect to the airframe to the inertial velocity of the wingtip, and that is captured by omega VE cross r tip, and that is your result. So then the next example that we're going to see is the propeller tip of an aircraft, and we want to be able to compute the inertial velocity of that propeller tip. And it is actually the same method than the one we just used before. And the first thing you need to do is to establish your reference frames, and that is the inertial frame E fixed to the ground and the body frame V fixed to the aircraft. The position vector r tip can be broken down into RV plus r hub plus r tip, and then it's the same method here. We know that the inertial velocity of the propeller tip is equal to the derivative of the position vector with respect to time, and that is with respect to the airframe. So all you need to do is to take the derivative of the vector components with respect to the airframe. And that is slightly more complicated because in here we have essentially a rotating frame within a rotating frame. So it starts with the translational velocity v, that is the translational velocity of the aircraft with respect to the airframe. And then we have to take into account the contribution of the rotation of the body frame with respect to the airframe, and that is omega VE cross r hub, and dr hub over dt with respect to v is going to be equal to 0 because it's a rigid body here again. And then for the actual propeller tip, there are actually two rotations that we need to take into account here. There is the fact that the propeller tip is part of the aircraft, and because the aircraft is rotating, that propeller tip is rotating with the aircraft, and that is what you see here. It is dr tip over dt with respect to v plus omega VE cross r tip. And then there's also the fact that the propeller tip is rotating or spinning with respect to the aircraft itself, and this is why dr tip over dt with respect to v is actually equal to dr tip over dt with respect to p, the propeller, plus omega pv, the rotation vector of the propeller with respect to the body frame cross r tip. So dr tip over dt with respect to p is going to be equal to 0 here again because it is a rigid body. The position vector of the propeller tip with respect to the hub is going to remain the same over time, so that derivative is equal to 0. And then you have your result at the bottom, which is the translational velocity plus the contribution of the rotation of the body frame of the aircraft with respect to the airframe, and that is for the hub. And then you have the contribution of the rotation of the body frame and the rotation of the propeller with respect to the body frame to the inertial velocity of the propeller tip. All right, that's it for today. Thank you very much. See you next time.